Hi, in this video we're going to define the physics quantity work. We're going to talk about how you calculate net work or total work done on an object, and we're going to talk about the work-kinetic energy theorem, which tells us how work changes the kinetic energy of an object. So let's start by defining what work is. The variable we use for work is a capital W. And you do work to an object when you apply a force to an object over a distance or over a displacement. So here in our little diagram, we have a box and it's being pushed or pulled across the floor over a displacement of delta x by some angled force F. So for a constant force, the way we define work is actually force times displacement times cosine of theta. F is the force, delta x is the displacement, cosine of theta is cosine of the angle between the force and the displacement. So another way you can think of work is multiplying F cos of theta times delta x, where F cos of theta is the component of the force that is parallel to your motion. The units of work are going to be joules, capital J joules, the same units as energy, which means they also have units of newtons times meters, or they have units of kilograms times meters squared per second squared, but joule is our standard base SI unit of energy. And when you do work, what you're going to do is you're going to change the kinetic energy of an object. You're going to speed it up or slow it down. If you apply a force in the direction of motion, you're speeding it up and you're increasing the kinetic energy of your object. If you're pushing in the opposite direction of the motion, you're slowing it down and you're decreasing the kinetic energy of an object. So this is kind of what work does. Work lets us change the kinetic energy of objects. Work is a scalar quantity, which means it has no direction. It's just a number, but it can be positive, it can be negative, or it can be zero. It's positive if you're increasing the kinetic energy of the object, which means your force is in the same direction as the motion. Work is negative if your force is in the opposite direction of the motion. You're decreasing the kinetic energy of an object. And if your force is perpendicular to the motion, then you're not going to be speeding up or slowing down the object. You're not changing the kinetic energy. You're not doing any work. Now you can still change the motion of an object. You can still accelerate it. But if your force is perpendicular to your motion, you're not changing its speed. So you're not changing its kinetic energy, doing no work. So let's do an example problem and try and calculate some work done by a few different forces. Here is our problem. Starting from rest, a 25 kilogram box is pulled 12 meters across a horizontal floor by a rope angled at 30 degrees above the horizontal. The tension in the rope is 80 newtons and the average frictional force is 50 newtons. So we need to find the work done by each force, which means we're finding force times distance times cos of theta for each force. So we're going to start with a free body diagram. I'm going to just sketch out a diagram of what's happening. It's a 25 kilogram box, so there's going to be a downward force of gravity, and mg is going to be equal to, it's going to be 25 kilograms times 9.8 meters per second squared. It's going to be 245 newtons. There's another force. We're pulling the box across the floor with a horizontal, with a rope at an angle of 30 degrees above the horizontal. So I'm going to just draw a dotted line here. There's a tension force this way, T, and it's equal to 80 newtons. Well, there's also probably going to be some normal force, although it's not going to be as large as the force of gravity. I don't know what it is, but we could calculate it if we wanted. And we have a frictional force, which is equal to 50 newtons. We pull our box a distance of, this is our delta x, and our box gets pulled a distance of It tells us it's 12 meters, so I'm going to label that in my diagram. Delta x is 12 meters. And we want to find the work done by each force. So to do that, we're just going to do F times d times cosine of theta for each force. Let me label my angle here, 30 degrees. So for the work done by, well, some of these are really easy, but let's start with the work done by tension. We do force, the tension force, be consistent and write it as a capital T, times the distance times cosine of our angle, and that's the angle between our force and our displacement. So that's going to be equal to 80 newtons times 12 meters times cosine of 30 degrees. We can just get the work done by plugging that into a calculator. 80 times 12 times cosine of 30. I'm going to make sure I'm in degree mode because my angle's in degrees. And I get 831. And my units are going to be joules because it's going to be newtons times meters. 831 joules. Work done by tension. And it is positive work because the force is in the same direction as the motion. Tension is trying to speed up our object. Well, we could also, well, let's just do the normal force next. The normal force is equal, the work done by the normal force is equal to the normal force, which we don't know what it is, times displacement times cosine of theta. Now, in this case, the normal force is perpendicular to our motion. Since it's perpendicular to our motion, the work done is 0. So the work done by the normal force is 0 because it's not speeding up or slowing down our object. That's easy. We can also use that to find the work done by gravity. Work done by gravity is going to be mg times delta x times cos of theta. But again, since theta is 90 degrees, since gravity is perpendicular to our motion, the work done is 0. And then we can do, our last work is the work done by friction. Well, we know it's going to be negative work because it's opposite the direction of motion, but let's just plug in the numbers anyway. Our angle is actually going to be 180 degrees, so the work done is going to be force of friction, delta x, cosine of theta, theta for friction, which is equal to 50 newtons times 12 meters times cosine of 180 degrees. Well, cosine of 180 degrees is just -1. So the work done by friction is just negative 50 times 12, or negative 600 joules. So actually only 2 of our forces are doing work in this problem. Friction is doing negative work, trying to slow our object down, and tension is doing positive work, trying to speed our object up. Before we answer parts B and C, let's talk a little bit about net work and the work-kinetic energy theorem. I'm also going to underline each of our contributing works. 1, 2, 3, 4 forces, 4 works. So part B asks us to find the net work done on the box. And the net work is just the total work done on the box by all of the forces. So there are actually 2 ways we can find it. The first way is to just calculate all the works from each individual force and add them all up. So we would get net work is equal to the sum of the individual works. And that's probably what we're going to do. The other way we can do it is if we find the net force by finding the sum of the forces and then add up the work. Find the work done by the net force by doing net force times displacement times cos of theta, where theta is the angle between your net force and your motion. So let's now that we know what the net work is, let's go calculate it in that problem. Part B is find the network on the box, and I'm going to do that off to the right. B. So we need to find the network. Work net is just equal to the sum of the individual works. So that's just going to be the work done by each individual force. We could also find the net force, but since we already have the individual works, let's just do that. It's going to be the work done by tension plus the work done by gravity plus the work done by the normal force plus the work done by friction. So our net work is just going to be, well, tension is 831 joules plus gravity 0. Normal did 0 work. And then friction did negative 600 joules. So the net work done on the box is equal to 831 minus 600, or 231 joules. Great. The third part is find the final velocity of the box if the, well, that's a mistake. It should just say find the final velocity of the box. However, in order to answer that, we need one more thing, and that is the work-kinetic energy theorem. Just like we had our impulse-momentum theorem, where the total impulse applied to an object is equal to the change in momentum, we have the work-kinetic energy theorem, which tells us that the net work done on an object is equal to the change in kinetic energy of an object. So in equation form, that is, net work is equal to delta K. We could also write it as force times displacement times cos of theta, F net, is equal to change in kinetic energy, which means that our net work is just equal to our final kinetic energy minus our initial, which means it's 1/2 mv final squared minus 1/2 mv initial squared. So this gives us a way to relate forces and distances, forces applied over distances, to speeds. Just like momentum, impulse gave us a way to relate forces applied over time to velocities. So if we use this work-kinetic energy theorem, we can then calculate the final velocity of our box. Actually, just the final speed. Let's go do it. Okay, part C is find the final velocity of our box. Let's do that over here. And we're going to use the work-kinetic energy theorem for that. So net work is equal to change in kinetic energy. Our net work is equal to 231 joules. So 231 joules is equal to K final, kinetic energy final, minus kinetic energy initial. Now, we also know that our initial velocity, the initial velocity of the box, is 0 because the box is starting from rest. So that means our initial kinetic energy is equal to 0. So that term goes to 0. And we get 231 joules is equal to our final kinetic energy. We can rewrite that as 231 joules equals 1/2 mv squared, and solve for v to get our final speed. We multiply both sides by 2 and divide by mass. We end up with 2 times 231 joules divided by mass is equal to v squared, which means v is equal to the square root of 2 times 231 joules divided by the mass, and the mass is given in the problem. It's a 25 kilogram box. So 2 times 231 divided by 25 kilograms, and we can just plug that into a calculator to solve it. 2 times 231 divided by 25, and we take the square root of that whole thing, and we get 4.29, actually 4.3, the correct number of sig figs, meters per second. So we've used the work-kinetic energy theorem to solve for our final speed. And just as a recap, work is when you apply a force over a distance and it changes the kinetic energy of an object. It can be positive, negative, or zero. It's positive when you increase the kinetic energy. It's negative when you decrease the kinetic energy. The net work is just the sum of all the individual works from each individual force. And the net work that is done to an object is equal to the change in kinetic energy of that object. So that lets us relate forces applied over distances to changes in speed using that Work-Kinetic Energy Theorem down at the bottom. Hope this was helpful. Bye.